Jacobi's identity. One easily shows that this odd x, odd y, this is really odd of xy. You can take this as an exercise. This really xy belongs to G. Okay. Now the thing is, this shows that this odd G, which you define by like this. This is defined by odd x, so that x belongs to G is a Lie subalgebra of and G. Of and over G. Okay. So now I define this center of G. It's really x belongs to G, so that xy is equal to 0 for all y belongs to G. And you can define like that. This is really x belongs to G, so that odd x is equal to G. This is called center of G. Okay. Now I define derivation of G. So this is defined as this. This is defined as, this is really D belongs to endomorphism of G. So that D of xy is equal to really dxy. This is plus x dy. This is for all xy belongs to G. So D is a linear map on G, so that D is a derivation. So this is called Leibniz rule. I have told you this in the beginning. Okay. So if check that if d1 comma d2 belongs to derivation of G, then this Lie bracket of d1 comma d2, this will also belongs to derivation of G. Okay. So this is a vector space. So thus derivation of G is a Lie subalgebra of endomorphism. Okay. Now as for x belongs to G, check this odd x belongs to derivation of G. So this is an exercise, and that is really this exercise use Jacobi identity. Hence what you get? Hence we get this thing, this odd G, subset of derivation of G, the subset of endomorphism. Okay. These are three important Lie algebra. K is either R or C. So then if you fix a basis on G, then this GLG is identified with GLNR or GLNC. So then GLG is a Lie group. So GLG is a Lie group with Lie algebra equal to small GLG, and that is really endomorphism. Now automorphism of G. this is really this phi belongs to GLG. So the phi is a Lie algebra homomorphism. That means phi of xy. This is really Lie bracket of phi x phi y, and this happens for all x values. And this is a Lie group. Okay, so this is a group. Okay, so called automorphism. Automorphism group of G. Okay. Now see, the thing is this phi, this automorphism of G is given by some equations. Okay, these are really, therefore this is a closed subset of GLG. Okay, so clearly automorphism G is a closed subgroup of GLG. Therefore by Cartan's theorem, automorphism G is a closed Lie subgroup of G. Lie subgroup of GLG. Now, exercise. So that this Lie algebra of automorphism G is derivation of G. So you have to use just a few properties of this exponential map. I think you should do this exercise. So this is not a difficult exercise. So Lie algebra of automorphism is derivation of G. Okay. Now I have told you one thing. Okay, I have told you one thing, that if this G is a Lie group, okay, and G has Lie algebra G, and suppose H is a Lie subalgebra of G, okay, then there exists a unique connected Lie subgroup. This is unique connected, yeah, Lie subgroup H. So that Lie algebra of H is equal to this small h. Okay, I will apply this thing. And for me, what is G? G is our GLG, and small g is our small GLG. It is endomorphism of G. And what is the Lie subalgebra? Lie subalgebra is RG. Here, RG is a Lie subalgebra of NG. So I will apply that fact. Since this thing RG is a subset of endomorphism of G, and this is actually Lie algebra of GLG. This implies there exists a unique connected Lie subgroup int G of GLG with Lie algebra of int G is equal to really RG. So int G is called set of all inner automorphism of G. These are called in I think called inner automorphism of G. Okay. So this is the thing. Now since this thing, since this RG subset of derivation of G, subset of endomorphism of G, this implies this int G will be a subset of automorphism of G, and so it will be a subset of this thing GLG. So these are three groups very important: int G, ort G, GLG. Correspondingly, algebras are art G, derivation of G, and endowment of G. Okay, so now, so definition. Actually, one thing I should tell you, remark. Okay, so one remark I must tell you, this int G, since int G is a subgroup of GLG, so int G may not have the subset topology of, may not may not may not have the subset topology of GLG, because this is a Lie subgroup, right? Always subset topology of GLG.
Muna,
Yes, sir.
do you mean, see, for example, on int G, you do have subspace topology of GLG, but
Yes, sir.
that does not make it a Lie group. That's what you mean.
Yes, that means that may not be the Lie group. Actually, by abstract theory, there is a Lie group, Lie subgroup, okay, which will correspond to the Lie subalgebra, but that topology may not be coming from the subset topology. Yeah, what you are saying, that is correct. Or in other words, int G has a subset topology. In that topology, it may not be a Lie group. Okay, so now, so definition. So let G be a Lie algebra over R, and let K subset of G be a Lie subalgebra of G. Okay. Now then this RGK, this is a Lie subalgebra of endmorphism of G. So then let, okay, so let K tilde, I told you that with the unique sorry, with the unique connected Lie subgroup of GLG with Lie algebra of K tilde is really RGK. Okay. Now, what is the situation? This RGK, since this RGK is really subset of RGG, and since this is subset of what derivation of G, the subset of end morphism of G. So this implies this K tilde will be really subset of int G, this subset of ort G, and this subset of GLG. So okay, this is my situation. So now I am giving an important definition. K is said to be compactly embedded in G if and only if this K tilde is compact. So this is the thing. Now remark, as I said that remark, harsh remark. As I said, K tilde may not always poses the subset topology of GLG. Okay, but of GLG. But however, if K is compactly embedded in G, then this K tilde will have the subspace topology of cells. And this is clear in the cases.
So, what exactly the problem if in such cases that using subset topology, K tilde or the int G may not be a Lie group, like will it be not closed?
Example you can see in the Helgason exercise. I think.
Yeah, you also give an example like as Sagar's discussion that it may not be a closed subgroup of GLNC. That the same problem occurs in this case also.
Yes, yes. But the thing is, if K is compact, the thing is something is a Lie subgroup. Suppose Lie subgroup of submanifold. Suppose K is a submanifold of, okay, let us see N. N is a submanifold of N. Okay. This map, embedding map N, suppose this is an embedding N from N to N. Okay, this map is continuous always. I is continuous.
Okay.
And but the inverse may not be inverse map may not be continuous. That is the issue. Okay. And I have told you that this example, for instance, if you look at this thing, figure 8 curve, and so that this curve will not touch this point. Okay. This is actually a submanifold of R2. But this, okay, so but this is okay. So if you look at this thing, okay, so you can actually map, you can have a map from R to this figure 8 curve. Okay, and so actually how you will give this manifold structure? Just by 1-to-1 correspondence with R. Okay.
Okay.
And this at this point actually this will have actually whatever neighborhood you will take. If suppose this has subspace topology of R2. Okay. If you will take at this point, if you whatever neighborhood you will take, it will have something like this part will be there and this part will be there. Okay. This will be something like this thing and this thing will be there.
Okay.
But in this, if you are borrowing the topology from R, then only this is also an open set, right?
Yes.
Okay. But this is not an open set of subspace topology of R2. So this inverse map is not continuous. And if N is compact, suppose N is compact, there is a theorem that if N is compact and a host drop, this is continuous and 1-1, automatically this inverse is really continuous. Inverse map is continuous. So that is the thing actually. Okay, so but if K tilde K is compatible, then K tilde will have the subspace topology. Okay, so what I am saying? Okay, K is said to be compatible energy, pendulum K tilde is compatible. So now, and definition. So definition. So Lie algebra G over R. Over R is compact. Is said to be a compact Lie algebra. Lie algebra. If and only if G is compactly embedded in itself. embedded in itself. Now let us see. Let us discuss something about what is this meaning about compact Lie algebra and why this is important. So discussion. Let G be a connected Lie group with Lie G is really G, and let H be a connected Lie subgroup Hello, are you able to hear me, sir?
Yes, now I can.
Oh, okay, sir. Where was I? This thing. So let G be a connected Lie group with Lie algebra of G is G, and let H be a connected Lie subgroup of G. So with Lie algebra of H is called H.
No, I can
We
see
know
your
that.
screen.
I can't see the screen. Ah, yes,
Okay,
now I can. Uh,
you can see now. Okay,
yes,
so
yeah.
here where was I?
Let H be a connected Lie subgroup of G with Lie
G.
algebra
Okay,
equal to little h. We know that capital add G, H to
G
GLG.
is a H2 is a group homomorphism. I am just restricting this RG to H. Okay. Okay. Now, okay, so okay, so I have told you in the previous lecture that if phi from G1 to G2 is a this is a group homomorphism. Okay, this phi G1 is a Lie subgroup of G2 with Lie algebra of phi G1 is really what? This was d phi G1, right? I have told you one of the where d phi is the derivative of the phi and G1 is the Lie algebra of G1. So I apply that thing. RG is a group homomorphism, and derivative of capital R is small r. So then RG is a Lie subgroup of GLG. GLG with Lie algebra small RGH. Okay. Now, since I have taken this G is connected, H is connected, I have taken. Since H is connected, okay, this RGH is connected, right? Hence, this RGH hence this RGH is connected. RGH is the unique connected Lie subgroup of GLG with Lie algebra small r gh. Now, thus h is compactly embedded in G. So if and only if this RGH is compact. Okay. So this is the thing. Now, so let H, okay, let us see, let X belongs to kernel of R G restricted to H, and that is my map. So this implies what RGX is equal to really identity. If I look at this thing, okay, so this implies RGX is equal to identity. So I look at this X exponential of X, this X inverse, okay, and this is really what? This is exponential of RGXX. Okay. This where this X belongs to G, I am taking. Now this will imply that now RGX is identity. This is really exponential of X. This X belongs to G. Since G is connected, exponential of the neighborhood, exponential of the Lie algebra will generate the whole group. So this will imply that xg x inverse is equal to G for all G belongs to G. So this implies this xg x belongs to, okay, this implies xg is equal to gx for all G belongs to G. So this implies x belongs to zg intersection h. Okay. Now conversely, if x belongs to zg intersection h, that implies x exponential of tx x inverse really, this is really exponential of tx because x belongs to the center, and this is really okay, odd of exponential of t rg x x is equal to really exponential of tx, taking derivative at t is equal to 0, and this happens for all t belongs to r. Taking derivative at t is equal to 0, we get rgx x is equal to x for all x belongs to G. This implies rgx is equal to identity. Okay. So that means x belongs to kernel of rg restricted to H. So hence kernel of rg restricted to H is really zg intersection H. So hence by this third isomorphism theorem, we will get that. So Rg is a map from H to GLG, and we know the kernel which is ZG intersection H. Hence we get this thing H by ZG intersection H. This is really RGH, and this is a Lie group isomorphism. Lie group isomorphism. Okay. Now, hence we have this thing. Okay. Hence this. Okay. So let us write a case then. So hence we get what? Suppose. Okay. Hence. 6 H is compactly embedded in G. in G, if and only if this RG H is compact, if and only if, and RGH is isomorphic to H mod ZG intersection H is compact. Okay, this is the thing. Now, if G is equal to H, say, then G is so if G is equal to H, then what I will get? G is equal to H. Okay, if G is connected, if G is equal to H, I will first what will get? Yes, G mod ZG is really isomorphic to RG. Okay, and this int G, I will get what? Int G is equal to RG, because okay, and G is a compact Lie algebra. If and only if this RG is compact, and if and only G mod ZG is compact. Okay. So everything happens in the connected G under the assumption G is connected. Okay, so if you think this characterization of compact Lie algebra, okay, or if you think this thing that whether H is compactly embedded in G, you may feel that this thing that this compact G is a compact Lie algebra, that depends upon the group G, but that is not the case, because what G is a compact Lie algebra or not, that depends upon the fact that whether int G is compact or not, and int G is completely defined in terms of Lie algebra. Okay, so it doesn't really depend upon the ambient group G. But if there is an ambient group, then it is easy to determine whether this G is really whether this small G is a compact Lie algebra or not. So corollary or observation corollary. Let us write corollary. So let G1, G2 be to Lie group, okay, with Lie algebra of G1 is equal to Lie algebra of G2. Okay. B2 connected Lie group, B2 connected Lie group, and so suppose this is G, say. For instance, if you to look at this SL2R and universal cover of SL2R, these both are connected Lie group, and these both will have same Lie algebra, isomorphic Lie algebra. Okay, so G, say, then this RG1 is isomorphic to really int G, and this int G also isomorphic to RG1, RG2, and this RG1 is isomorphic to G1 in mod ZG1, and this is isomorphic to G2 mod ZG2. So okay, so this is the useful fact. Similarly, I can write another corollary. So let G1, G2 be two connected Lie groups with Lie algebra of G1 is isomorphic to Lie algebra of G2, and this is G, say. Okay, so let K1 subgroup of G1, K2 subgroup of G2, K1, K2 connected, and Lie algebra of K1 is isomorphic to Lie algebra of K2, K. So then, so this G1 in mod J K1 is K1 ZG1 intersection Q1 is add G1 K1. This is isomorphic to R G2 K2, and this is isomorphic to K2 ZG2 intersection. So these are the these are some simple observations, and this will be very useful in later. Okay. Now, now important thing. Suppose let let us see discussion. So let G be a connected Lie group and H be a Lie subgroup of G, but H is not connected. H be a Lie subgroup G, and H is not necessarily connected, and H is not necessarily connected. If H is not necessarily connected, okay, and suppose RGH is compact, which is the condition in the Riemannian symmetric pair case. Suppose RGH is compact. If G is a Lie group, then its connected component G0 is always closed and open in G. These are some facts. If G is a Lie group, you look at the connected component of identity inside G, that is G0. This is always closed and open in G. So this suppose RG is compact, then as RG H0, okay, as H0 is closed in RGS. Therefore, RGS not is compact. It's compact. Now, as RGH not is equal to really RG. Sorry, I should this thing. RGH not is equal to RGH not. So this requires little bit work. You can do that. Okay. This is really, you can assume that, or you can take it an exercise. RGH not is equal to really RGH not. Therefore, this RG H not is compact. Now we are in the previous situation where G and H not both are connected and RGH not is connected compact. Since both G and H not are compact, by previous discussion, okay, this Lie algebra of H not is equal to Lie algebra H equal to H, say, okay, is compactly embedded in G. Embedded in Lie algebra G. So the conclusion, if RG H is compact, then this the Lie algebra of H is compactly embedded in G. And I am writing this. So, conclusion. Let G be a with Lie algebra of G is equal to G and H be a Lie subgroup of G with Lie algebra of H is equal to H. Suppose this RGH is compact, then this H is compactly embedded in G. So this is the thing. Now I want to give some examples. So example, suppose so let G be a compact Lie group, then G naught is also G naught is also compact Lie group because G naught is closed in G Lie group. Then this G is equal to, okay, then by this definition, okay, so where I am saying, okay, I have said that if G is connected, G is compactly algebra if and only if RG is compact and G mod ZG is compact. Since G naught is connected, okay, since G naught is connected and compact, therefore you can apply this formalism, and then G is equal to this Lie algebra G naught, which is really Lie algebra of G is a compact Lie algebra. Okay, hence this SON, this SUN, UN, SPN. So direct sum of SON and SUN, UN and SPN. These are all okay. So let us say SON. These are compact Lie algebra. Are examples of compact Lie algebra. Converse is also true. So fact, any compact Lie algebra is a Lie algebra of a compact Lie group. Okay, if you look at this example, okay, for proof you can see algorithm for, so proof of this fact you can see algorithm. You can look at this example, for instance, this R is Lie algebra of S1 and as well as R, right? Lie algebra of R is really R, but R is also a Lie algebra of S1. Therefore, R is a compact Lie algebra. Similarly, this Rn, Lie algebra of S1 cross S1, this is a compact Lie algebra. So now I want to give an example of non-compact Lie algebra. let G is equal to really SLNR or say SLNC. Then if you look at this ZG, this is really identity if n is odd, and this is plus minus identity if n is even. I am using this some fact that ZG is equal to lambda times I of this. Okay. Okay. Since ZG is compact and G is non-compact, this implies G mod ZG is non-compact, right? Because of this first proposition I have said. If G mod G is compact, since G comma G will be compact, and therefore this will be contradiction. I am using one of our proposition. Here we are using one of our proposition, previous proposition. So G mod therefore, and this was equivalent to the fact that whether G will be compact or not. Therefore, G is equal to really small SLNR or SLNC is a non-compact real. Okay, so now we have this thing. You take this if you MNC or MNR. If I will ask you to produce a bilinear form, symmetric bilinear form on MNC or MNR, you will say that this is my bilinear form. B of some B tilde, so E of F is really trace of EF. So this is a symmetric bilinear form on MNC or MNR. You can also, if B is a subset of MNC or MNR, then this is also a symmetric bilinear form on this MNC, right? EF belongs to B. Now, you know this in RG is a subspace or subalgebra of endomorphism G. Then you can really produce a bilinear form on RG, B tilde RX, RY. This is the actual trace of RX, RY. This is a bilinear form on this RG, but you can use that to produce a bilinear form on this Lie algebra G, that is called killing form. B of XY is called trace of RX, RY, and this is called killing form. And this is a very important bilinear form. So I define this called killing form. So let G be a Lie algebra over K. Okay, where K is really R or C. This K is equal to R or C. So we define a symmetric bilinear form B from G cross G to K given by this thing B of XY is equal to trace of RX composition RY. This XY belongs to G. So B is called the killing form of the Lie algebra G, or B is called killing form of G. Now definition. And remember, this G is a Lie algebra over K. K is R or C. So I am not assuming that only G is a Lie algebra over R. So a Lie algebra G over K is called semi-simple if and only if it satisfies one of the following equivalent conditions. So first is really G, the scaling for B of G is non-degenerate. Second thing is G is direct sum of simple ideals of C. So you can take one of the thing as a definition. Okay. So another definition. A Lie group G is called semi-simple.
Muna, what is non-degenerate?
Oh. So non-degenerate, this I usually define, okay, non-degenerate. So if B is called non-degenerate, if this B of xy is equal to 0 for all y belongs to G, then this implies x is equal to 0. Okay, so this is that thing. And here this B is symmetric, so that for in one coordinate it will be sufficient.
Yes.
Now definition. So Lie algebra, Lie group G is called semi-simple if and only its Lie algebra G is semi-simple. So clearly, if G is a simple, so if G is a simple Lie group, then this G is semi-simple. So similarly for Lie algebra, if a Lie algebra is simple, then it is also semi-simple. Okay, so that is the thing. Now, there's some properties of killing power. So let G be a Lie algebra over K.
Muna,
Yes, sir.
definition of simple Lie group is what? Its Lie algebra is simple.
Yes, sir. By the way, I didn't tell you this. You can see the equivalence of these two. You can, for that you can see Helgason or Humphrey. So for proof of these two things, that these two things are equivalent, you can see Humphrey or Helgason. For Lie algebra, this Humphrey is a very good book actually, and it is really very well written. And from uh, if you, it is also well written from Helgason actually. In Humphrey is a very good book for Lie algebra. Okay. So let G be a Lie algebra over K. Okay, so then first it has two things. Let phi belongs to automorphism of G. Then this B of phi x, phi y. Oh, sorry, I should read B of phi x, phi y is equal to B of xy. So with killing form. Okay. This xy belongs to G. So second thing is let D belongs to derivation of G. This thing B of dxy is equal to minus of B x dy. Okay, this x comma y belongs to G. Third thing is C will B of this x y z B of x y. So this is x y z belongs to G. Okay. This property is called associativity of the killing point. This is called associativity. The reason is if you for a associative Lie algebra, associative if x something is in associative Lie algebra, you have this thing xyz is equal to xyz. Now instead of this bracket, you put the Lie bracket, then and then you apply the killing point. So for that reason, this is called associative Lie algebra. Associativity. This property is called associativity. So proof. So let us see. Proof. So first A, let phi belongs to this automorphism of G. That means if you look at this phi x y, Lie bracket of x y, this is really phi x, phi y. So using this thing, you really is phi composition odd x y. This is really odd of phi x composition phi of y. Rajesh Bhaiya, is it clear?
Yeah.
So this is so here from here you get phi of odd x is equal to odd phi x composition phi. Okay. Phi is a automorphism, so this phi is an invertible map. So you will get odd of phi x is equal to phi composition odd x composition phi inverse. So this is a very important relation. So now B of phi x phi y. So this is really what? Trace of odd phi x odd phi y. This is really trace of phi composition odd x composition phi inverse. This phi composition odd y composition phi inverse. Okay. So that is really trace of phi composition odd x odd y composition odd y phi inverse. And trace is conjugation invariant. So that is trace of odd x odd y, and this is really B of xy. So this is clear. So we have done the proof of A. Now I will do the proof of B. So B. So let D belongs to derivation of G. Okay. So let D belongs to derivation of G, then e to the power TD, and derivation of G is Lie algebra of automorphism G, right? So e to the power TD belongs to automorphism of G for all T belongs to R. That then I can apply the by A. I can apply the A. So by A we get this B of e to the power TD x, okay, e to the power TD y is equal to B of xy, and this happens for all T belongs to R. So our taking derivative at T is equal to 0. At T is equal to 0, we will get this thing. We get this B of dx y plus B of x dy is equal to 0. So that will give you B of dxy is equal to minus B of x dy. Okay. Now see. So for x belongs to G, We know that this Rx belongs to derivation of G, because now by B we get this thing, B of Rx y z is equal to minus B of y Rx z. So this implies this B of xy z is equal to B minus B of y. This is really xz, right? Now since B is bilinear, I will take minus sign to this thing, and this Lie bracket is also, if you will change the order, that will give you a minus sign, and I will use that thing. So I have to just change the order of the Lie bracket, bzx. Now I will write this thing bzxy, because this is really bilinear form, symmetric bilinear form B. So B of this is really zx y, and hence this B is really associative. So this is a thing. Now I will this form is perfectly fine, but sometimes something is useful like this. If you look at this thing, B of xy, this is equivalent to the fact that B of xy z plus B of y xz, this is equal to 0. So sometimes people use this form also. So we will use that thing. Now I have 15 minutes. I will prove one proposition, then we will finish it, everything. Okay. So this is a very important proposition, because tomorrow in next lecture you will see that what is the proposition. So let G be a Lie algebra over R, and let this K be a compactly embedded subalgebra of G. Subalgebra. Then the scaling form BG, if you restrict to K cross K, this is actually negative. But negative, I think, to be very clear, I will write this negative semi-definite. Okay, and so moreover, BG in K cross K is BG restricted to K is negative definite. If and only this thing K intersection ZG is zero. Okay, proof is a proof of, probably some of you have seen that. Since K is a compactly embedded subalgebra of G, there exists a compact subgroup, compactly subgroup K of GLG or OT G. Okay, K of OT G with Lie algebra of K is really RGT. Now we fix a K invariant. Okay, since K is compact, we fix a K invariant inner product this thing on, and this is possible. I have shown you this example. Okay, so let X belongs to K. let x belongs to k. This implies this RG x belongs to this RG of k. Okay. Now this implies e to the power t RGX. This belongs to k for all t belongs to r. Okay. As this inner product is k invariant, hence this for any y comma z belongs to g and x belongs to k, we have this thing. Because e to the power t RGX belongs to k, so we have this thing e to the power t RGX y, e to the power t RGX z. This is really what yz. Okay. So now if you take derivative at t is equal to 0, and with respect to t you have to take with respect to t at t is equal to 0. So that we will get this thing RGX y RGX RGX yz plus this y RGX z, this is equal to 0. Okay. This is really RGX y z. This is equal to minus of y RG x. I call this as star. And here what is the condition? X belongs to k, y comma z. This belongs to g. And this says that this RGX is skew symmetric. Yes. This RGX is skew symmetric. Okay. Now, so let E1, E2, En be a basis of G. Now, what is B? Okay. For X, let X. Okay, so let X belongs to K. So B of X is so trace of RX composition RX. This is a real trace of RX square. And this is summation of, by definition, this I is equal to 1 to n RX square EI. Be an orthonormal basis. Be an okay ONB orthonormal basis. ONB means orthonormal basis. Okay. So this is the thing. Now I will apply this star here. So this is really, there will be minus sign. I is equal to 1 to n RX EI. So this is really minus of I is equal to 1 to n. So RX EI norm square, right? And this is always less than equal to 0. So here I am using this star. So now, okay, this is always hence BZ restricted to k cross k is negative semi-definite. My God, I'm running out of time. Okay, so this thing Bxx is equal to 0 if and only if this is RG. This is really RG. Okay. RGX EI is equal to 0 for all 1 less than equal to I is in n. if and only if this Rg is x is equal to 0. So this if and only if this x belongs to ZG intersection K. Hence, B G restricted to K cross K is equal to 0 if and only is negative definite. If and only if if and only if ZG intersection K is equal to 0. Now one application. Okay. So let us say discussion. So let G be a compact Lie group. So with Lie algebra G. So then G is a compact Lie algebra. Then G is a compact Lie algebra. Hence, killing form B on G. B on G is negative semi-definite. It's negative semi-definite. Now, so killing form is negative definite. If and only if ZG is equal to 0. This thing ZG is equal to 0 because I am applying this result here. K is equal to G. Everything is here. Actually, K is equal to G. I am applying this proposition. So this is really if and only if this is ZG is discrete. Now G is a compact Lie group and ZG is a closed subgroup G. Therefore, ZG is compact. Okay. So if a compact group is discrete if and only ZG is finite, right? So hence we get the following proposition. So let G be a compact Lie group with finite center. Then killing form B on G is negative definite. And this B and this G is semi-simple. Once the killing form is negative, then this is semi-simple because that is an inner product. Negative of that is an inner product. So killing form is not there. Therefore, G is semi-simple. So with this, I will stop this thing, and I will be happy to answer any question. In the next lecture onwards, we will define something called orthogonal symmetric Lie algebra. And whatever I have discussed today, this will be very handy. And we will define this compact symmetric space, non-compact Riemannian. No, sorry, symmetric space of compact type, non-compact type, Euclidean type. Then we will give some examples, and then we will prove a decomposition theorem. Okay, in the next lecture. Is there any question? So you can ask me.
I think what one would like to know is how does negative definite implies non-degenerate?
Okay, so suppose
I am saying
This-
this, otherwise semi-simple will not follow.
Yes, sir. Yes, sir. I think. Okay. Suppose this B is negative definite. Definite, and definite on G. So let x belongs to G. Okay. Now that means. So what is the meaning of negative definite? If bxx is equal to 0, this will imply that x is equal to 0. Okay. So this implies this is B is semi-simple. Sorry, G is semi-simple. This is trivial, I think. So is it okay? Hello,
Yeah,
sir?
for me it's okay.
Yeah. I was surprised that. Okay, so is there any question on Anway or Manali or something? Somebody who is there?
No, it's fine. I don't have any questions right now.
Tapendu?
No, the last part
Okay.
is not okay. The
Last part.
non-degenerate part. So we have to show if bxy equal to 0 for all y, then x equal to 0.
Okay, so since this is
Oh,
definite.
okay. Sorry. Sorry.
Okay. Okay, let us
Muna,
disconnect. Yes. Yeah.
what is the significance of the scaling form?
Killing form, it is
This,
a very important.
yeah.
Yeah. Actually, I cannot tell you. You will see later. Killing form is the
Okay.
thing actually very important of
This
this.
something like negative of this, like a metric or something.
Actually, yes. In the see the thing is, yes, Riemannian symmetric space is really it will be said to be a compact type. Okay. If the killing form on this P actually restricted to P is negative definite. Okay. If you will take this minus of B, that will be an inner product on this P. Okay. And killing form will be RG invariant. And so that will induce a Riemannian metric on this Riemannian symmetric space of compact type. And for non-compact type also, you will use this killing form to induce a Riemannian metric on the symmetric space. And apart from this, you know that see this killing form will be very instrumental in using this root space decomposition. Okay. This is very important bilinear form actually.
Okay. Okay. Thank you.
So you have recorded Rajesh?
Yeah, I think I was little bit. I actually forgot, so I came little bit 5 minutes late. So after that, I
I
recorded.
will next time onwards I will call before you 5 minutes.
So
Good.
so
Yes.
I'm ending this recording.